right. So welcome to this. In this video, we're going to discuss sort of briefly what happens if we have damped motion. So recall just sort of that last time that if we have a simple spring, which we're just going to call undamped, with mass or with an object of mass m attached, then the movement can be modeled by this differential equation for k some positive constant. And if we look at the solutions of this, right, we're just going to have mr squared plus k equals 0. So r is equal to plus or minus I times the square root of k over m, and y is equal to c1 times cosine of square root of k over m t plus c2 sine of square root of k over m t. Okay, so one just sort of observation, note that in this model, when we have these solutions, they're sort of cyclic or periodic. So it's periodic motion. And once we sort of have our RC1 and C2, it's never going to sort of stop moving, and it's never even going to slow down. You know, I mean, it will from moment to moment, but not in the long run. As soon as it gets going, it stops, or it keeps going, and it doesn't really change its behavior at all. So today, we're going to sort of change that, and we're going to talk about damped motion. So a damper is usually a device you put on a spring to make sure it doesn't move too fast. So if you've ever seen those sort of doors where you open them and then they kind of can't slam, they might close automatically, but they'll do it slowly. That's because they have a damper attached. So in this model, the damper sort of introduces a damping coefficient, which again, we're going to assume is positive. And with this, we're going to sort of have the total force acted on the spring is going to our damper is going to oppose movement, right? It's a frictional force, and it's actually the amount of force it exerts is directly proportional to our current velocity. Yeah, so we can see, you know, proportional to our current velocity. So again, if this is our total force, right, if F is, you know, total force of object at the end, then we know that we're still going to have M, or force is equal to, you know, M, which is our mass, times our acceleration, which is y double prime. Where again, y is our displacement. So putting that all together, we have our free damped motion equation. And says sort of the following. So given an object of mass m, attached to a spring with damping coefficient, or I guess I'll say spring system, so damping coefficient C and spring constant K, then the displacement y satisfies, you know, the following differential equation: mass times y double prime plus c y prime plus k times y equals 0. And note this free here, I'm not going to say much about free versus, you know, forced motion. So free means that essentially we set this equal to 0. It's a homogeneous linear equation and not a non-homogeneous one. So if it's, you know, forced motion, that means we'd have some outside, like motor or something that's applying a force. Okay. So we already know a lot about equations of this form. So let's just go ahead and you know, look at the different possibilities. The one constraint we have here, right, are M, C, and K are strictly positive. So we're going to look at general solutions to free damped vibrations. So we should already know how to, you know, solve this, at least if I gave you a specific one, right? Like I just would look at the characteristic equation. And, you know, we don't know anything about these values, so really all we can do is, you know, plug them into the quadratic formula, and we'll get r is negative c plus or minus the square root of c squared minus 4mk, all over 2 times m. Okay, so there's a couple different cases, and these all sort of go by special names, and I'll sort of say a little bit about them. So the first case happens when C equals 0. And we know in this case, looking at that, okay, C is going to go to 0, so we're just going to get R is equal to plus or minus the imaginary unit I, right? Because M and K both have to be positive, so we have negative that over the square root, or times the square root of K over M. This case is, as we saw, it's undamped motion. And if we let omega equal that, the solutions are so sort of the key thing to note, solutions are purely periodic. The next case, so all these other cases, C is going to be strictly greater than 0. But we have actually three sort of cases for this term here, C squared minus 4mk. So the next case is going to be where that is C squared minus 4mk is negative, so we still end up with complex roots. This is what's known as underdamped motion. And in this case, right, C squared minus 4mk is going to be negative, and we're taking the square root of a negative, so we're going to end up with negative C plus or minus I times 4mk minus C squared over 2m. So solutions like this are going to have sort of two parts. We're going to have e to the negative c over 2m times t. So this is going to sort of represent a decay. And then in here, we're still going to have sine and cosine, where omega is this guy. These solutions are sort of quasi-periodic. So if we sort of looked at a graph of them, they would sort of have, a sinusoidal thing, but it's going to die out. The next case is what's known as critically damped. And this what happens is this is the case when c squared minus 4mk is 0 or equivalently, c is twice the square root of mk. This case, we have a repeated root of c equals negative, or of r equals negative c over 2m. And we know what happens in that case. So I've been told that in like a lot of engineering applications, this is sort of what you want your springs to be at least sort of. They want to be close to critically damped. If you look at solutions, they've lost their sort of, they're non-periodic totally. They just have sort of a decay factor. So they just sort of look something like this. And the main difference between what the solutions do in this case and the next case is just sort of how fast they sort of reset. So the next case is c squared minus 4mk is greater than 0. This is what's known as overdamped. And this is going to have, two distinct real roots. And sort of as I sort of mentioned, if you look at critically damped, it will still sort of decay, but usually slower is the sort of only issue. So when sort of understanding these cases, I like to sort of imagine that I'm in like a car, and what happens if I go over a bump to my suspension in either case. So if you have strictly undamped, you hit a bump and your car just keeps wiggling up and down forever until I guess you hit the next bump. So you definitely don't want undamped. Thankfully, it's near impossible in practice. Underdamped, isn't too bad depending on how damped it is. You could decay, but you're going to wobble up and down possibly for a while. Critically damped is probably what you want because it's going to sort of even the car out, as quickly as possible. And you definitely also do not want overdamped because, if you're really, really overdamped, you hit sort of a bump and your car is just going to sort of stay in the low position, slowly rising up, over the next several miles. All right, so let's end this video with just a quick exercise / example. So this is going to have multiple parts. I'll do the first part, and then you guys can try out the other two parts on your own. So we're also going to sort of switch things up and do things in imperial units. So a 64, pound weight is attached to a spring system stretching the spring 6 inches. to, the new equilibrium. So a dash pot, which is just a type of damper, provides a damping force of C pounds for each foot per second of velocity. Okay, so this is our general setup. Part A, we're just supposing that C is equal to 30. The spring is pulled down one foot and released. Set up an IVP modeling the situation. All right, for part B, just want to know, is the spring system in part A overdamped, critically damped, or underdamped? And part C, the dash pot is then modified to be critically damped, which I guess is somewhat of a spoiler for the answer for part B. The spring is stretched 18 inches and thrown upwards with a velocity of 2 feet per second. And again, just set up an IVP. Yeah, so don't necessarily solve the IVPs. That's a lot of work and not really what we need to be practicing here. We will still assume you know how to solve the IVPs. In fact, we're going to devote a lot of time to an alternate method of solving them. But yeah, okay. So like I said, I will do part A. Okay, so a couple things to know, especially for any foreign students. So 1 foot is equal to 12 inches. And also the thing, even for my American students, because I often forget this, but a pound is not a unit of mass, it is a unit of force. The other thing we're going to need is the gravitational constant in terms of imperial units, and we're just going to use 32 feet per second. Okay, so that's sort of some background. So let's go ahead and solve this. So these imperial problems are sort of, one part's easier, one part's slightly harder. So we actually have to go ahead and solve for mass. So, so we apply 64 pounds of force. So we have m times our gravitational constant g is equal to negative k, or k rather, times 64 pounds of force. No, just 64 pounds. Sorry. K was, yeah, K is for the next part. So we just go ahead and we get m equals 64 pounds divided by, that should be second squared, 32 feet per second squared. So we have a mass of 2, and there's actually a name for this unit. They're called slugs. So m equals 2 slugs. And we can't just use 64 in the equation because the units would be messed up in our differential equation. We have to divide by this 32. Okay, but now we can go ahead and solve for k. We have that our displacement times k is equal to our force, which is 64. So 64 times 6 inches, so half a foot, and k equals 128. We're just told that our c is 30, so we can at least set up part of our answer. We have 2y double prime plus 30y prime plus 128y equals 0. We're then pulled down 1 foot and released. So pulled down 1 foot, remember down is positive, so y of 0 equals 1. And released, remember whenever you see that, that means that our initial velocity is 0. And that is our answer there. So didn't ask to solve it, just wanted to set up the IVP. All right, so go ahead, take a minute to try to solve parts B and C. And okay, hopefully you paused it and did so. So for part B, we wanted to know if it was overdamped, critically damped, or underdamped. And from part C, we can probably eliminate critically damped, but let's see why. So if we look at our characteristic equation, and we just plug it into our quadratic formula, We don't necessarily have to do this, but I don't know. This is kind of how the quadratic formula is how I remember this discriminant part. Plus, you're usually going to have to do it to solve the equation anyway. So 30 squared is 900. And then if you're really good with powers of 2, you might know that 128 is 2 to the 7th. So this whole thing becomes 2 to the 10th, or 1024. Note that this term is negative, so our answer is underdamped. And that answers this one. So for our next part, we want to see for what C are we going to get to make it critically damped. So looking at this part, right, we have C squared minus 4 times K times M equals 0. So C squared minus 4, K is 128, and M is 2. C squared equals 1024, which is 2 to the 10th. And so C is 2 to the 5th, or 32. We already solved for our mass and, M or a K for the first part, so we don't have to redo that. And now we can just go ahead, look at that additional 18 inches, and we're thrown upwards with a velocity of 2 feet per second. So combining all that fact, we get our answer, which is 2y double prime plus 32y prime plus 128y, where y of 0 equals 18 inches divided by 12 is 1.5, and we're thrown upwards with a velocity of 2 feet, so y prime of 0 is going to be negative 2. And that's our answer.